Everybody can see my screen. Start the presentation here. Oops. Going to the end from the beginning. All right. Hi, everybody. Thanks well, thanks. First, I'll start with thanks to everyone on the call right now, really. This has been a fun experience for me. I think it's been a scientifically productive experience for us all. Spending the last 4 years really focused in on this question of compound identification and, from a bigger perspective than that, how we can work together as labs, each with our own projects, with our own thoughts and ambitions, and biological questions that we're addressing to move the field of metabolomics forwards. Both in the context of compound identification, which has been our specific focus, but also in a larger scheme. And it's been great. And we thank the NIH for their vision in helping make that happen. Today, we all started out the CIDCs at least divided into these experimental cores and computational cores with projects and working groups in there. And, it was my impression that as things moved along, the lines really blurred between what's an experimental project, what's a computational project. One informs the other. You can't do what you need to do without both. So, the division that we started with turns out to be a little bit on the arbitrary side. And while it helps you, frame your projects, really, it's all part of the same picture. So we'll talk about some of all of these things that we've done here in Michigan. So I'll start out with something that Brady told you a little bit about yesterday, which is, what can we do to help identify unknowns, from an experimental standpoint, right? And most of the time when we're doing metabolomics, we are content to work with a method that can be used for quantitation, right? And that's essential because we need to detect features we need to quantitate features in usually a large number of samples, have sufficient number of biological replicates to study whatever it is, that we're trying to understand, whether we want to understand, biomarkers for disease, whether we want to understand, metabolic flux. We need replicates, and we need something where we can analyze a sufficient number of samples to get the data and move forwards and do statistical analysis. But it was our supposition that the conditions that are used for that, and we move ever quicker with our LCMS runs, and that's to some extent a good thing in that it allows higher throughput. But the conditions that we run with for general purpose metabolomics may not be quite optimal for identifying compounds. And generally, we just use we use the same LC conditions that we would use for untargeted metabolomics to try to identify our compounds. And that makes some sense because we'd like to be able to align things by retention time, which is an essential piece of information when we're doing LCMS or GCMS. But there are limitations that imposes on the information that you get out. And compound identification, of course, is the ability to identify compounds is limited by many factors. Of course, if we have standards, that's great, but we don't always have them. Spectral libraries are also a very good thing when we've got a compound that matches what we're trying to identify in a library, but those libraries may be incomplete. The other factors are the information content of the spectra that we've got, and the signal to noise in that spectra. If you have a noisy mass spectrum, it doesn't matter if the spectrum matches something that's in your library or not, you may not be able to identify it. And so another observation that we found is that high quality MS-MS spectra are not always obtained for all the features that you can detect in an untargeted metabolomics run. That can be because maybe a molecule doesn't fragment well, or it can be because it's at low abundance and there isn't sufficient signal there to go after an identification, even though you might be able to detect and even quantitate that feature. And so our thought was that we might be able to improve the situation by optimizing chromatography for compound identification first, rather than quantification, and then go work backwards and say, all right, once we've identified everything that we can in a representative sample, can we find it in the sort of conventional run conditions. And so this work is partially been published in Analytical Chemistry last year, and a lot of it's been done by grad student Brady Anderson. Okay, so Brady showed you a little bit of what he found. I'll just take a little bit more time to go through it. So a typical run LCMS conditions might be something on the order of 20 minutes, but we easily can access runs an hour 20 minutes long. And while that sounds prohibitive, if you are going to run 100 samples that way, to run one representative sample, where most of us do most of our identification work on a representative sample rather than trying to do MS on every single sample and do all the identification in every sample, this workflow becomes much less cumbersome. And so it turns out that by lengthening the gradient, even you can do better when you use a longer column with a long gradient, but even using the same column that you might use to do a standard analytical separation, a 15 or a 10 centimeter column, you can improve your compound identification substantially by lengthening out the gradient, performing a better separation, and sort of a concomitant effect of that, as you lengthen your gradient, you also you're able to resolve lower abundance features from higher abundance features, and at least mass loading, overloading and the resulting ion suppression becomes a little bit less of a problem. So we found that as you use lengthened gradients, you are able to load a bit more sample on your column and improve your identifications as well by being able to access more of those low signal to noise features. Now, there are compromises here, of course, features that are perhaps well resolved at a lower loading amount might be a little bit less well resolved, but we still I feel that the net benefit, there's a net benefit to this loading, this increased loading capacity. And by using retention time at peak center, you can often identify the feature that you're looking at in the conventional run conditions. And this works for both Hillock and reverse phase separations. And another thing, which is been around for a while, but we're still surprised to see that it's not universally used, is iterative MS acquisition. And so by not limiting yourself to a single MS run on a sample, but by doing dynamic exclusion of precursors that have already been acquired in prior runs, you can really get lower in the sample. And it's important to say that while this really does improve your compound identifications, it doesn't achieve everything that you could achieve by lengthening gradients and increasing your mass loading. And so by optimizing chromatography, we're able to substantially increase our identifications. And so these identifications here are just matches to a NIST spectral database at a specific score threshold with other criteria applied, a minimal entropy score and a minimal relative abundance in the spectrum. There are other factors that you can use, and we'll talk about that a little bit longer. So, okay, how does this look? So this was just a study of a plasma sample. So when you look at all of the identifications that you get, a certain portion of the identifications can be removed because they look like a background ion. The spectrum is noisy based on certain criteria, or there just aren't enough fragment ions in the spectrum to attempt to match. And then you can look at the identifications and break them down into the usual MSI levels if you choose to do that, and say, how many are a MSI level 2 match, how many are an in-source match without sort of allowing for neutral losses, and then how many are a compound class, sort of an MSI 3 level match. And these matches are valid, as there's, and we'll talk about that a little bit later on. How do you determine whether an identification is valid? Well, there's a lot of different strategies there, but right now, there's really no substitute for sort of empirical estimation or empirical assessment of your false discovery. In other words, using in-house libraries to say, was a match that I made that was reported by an MS match with meeting the score criteria that I accepted, does it match mass to charge retention time MS spectrum for authentic standard? And using the compounds that we are able to assess. We know, as others know, that false discovery rates are higher in metabolomics than they would typically be in many of the other omics sciences. But by setting appropriate score thresholds, you can achieve FDRs, at the level that you want. And so regardless of what level of false discovery you accept, the modified conditions are clearly superior in terms of the identifications to conventional run conditions. And so setting these correct conditions, these thresholds to achieve that level of FDR that we want is another really essential thing that we've worked on that I don't think we have a final answer to, but we'll talk a little bit more about later on. So just another way of looking at these. Okay, well, what about the unknowns? We'll talk about the what about the unknowns question a couple of times, but that's a question that we'd like to address. So of those remaining 2,000 unknowns or 3,000 unknowns, how many of them are features that we would like to spend time working on versus how many of them are features that are less likely to be identifiable and are not worthy of further detailed effort? Well, of course, a valid way of looking at that is in the context of a biological project. Generally, you don't want to spend a lot of time trying to identify an unknown that has no biological signal of interest. So if you're doing a study between two groups, you're not as interested in the unknowns that are not differential. The unknowns that are differential are of greater interest. But that type of approach, I feel, has limited our success annotating unknowns overall and making the work for other labs easier. So if you find an unknown that is not necessarily interest in the context of your project, it may be of interest in the context of another project. And so sometimes there is justification for careful classification of the unknowns that you have in a data set, be they differential or not. And by using this machine learning approach that Brady looked at by assessing features that are unknowns and looking at various criteria such as their entropy score, their mass to charge, their retention time, their relative abundance, and other parameters are possible as well, classifying whether a feature that is an unknown looks like or shares characteristics with other features that are knowns versus shares characteristics with only features that are unidentified in the data set. We can classify our unknowns into features that are sort of the lower hanging fruit. We call them the high priority unknowns versus those that are, that don't share characteristics with known features. And obviously this is not a perfect test, but we've applied this in a few different contexts, including the context of the Unknown Lipids project. And we feel like as far as prioritizing unknowns in general, it's an interesting strategy that can at least help you decide when it's worth spending effort looking at orthogonal techniques. Okay, so that's fine. We can do that with one-dimensional standard separations just by running longer gradients, loading more onto the column. But can we do better? And so Brady briefly touched on this topic as well that he's been looking at. And so our premise was that if one-dimensional separations are good, prefractionation, i.e. offline two-dimensional chromatography, may be even better. And so what does this look like? This looks like a semi-preparative LC separation, taking advantage of the fact that we generally aren't sample limited, especially when we're talking about looking at representative pooled samples for a particular sample type in a given study, that we can load more sample if we only can extract more useful information from it. So typically we're looking at using a 10 millimeter inner diameter column, runs at 3 to 5 milliliter per minute, so it can be run on a conventional LC, maybe with some modifications to your autosampler to allow a larger injection volume. You can do automated fraction collection. This can be done easily in a 96 well plate or in individual vials. You can dry fractions, reconstitute them in an appropriate solvent, leaving them in the same 96 well plate or moving them to autosampler vials, and then do an orthogonal method of LC-MS-MS. And this is just an example of what a chromatogram looks like for a human urine extract run on reverse phase in the first dimension in your semi-preparative mode, and then Hillick in the second dimension. Brady has lately been looking at fecal samples because they're interesting, contain lots of unknowns, but are certainly of high biological importance. Looking at a couple of different modes of chromatography. Here's a reverse phase bihelic separation, and you can see what you might expect. The earlier fractions in the reverse phase dimension contain more of the polar compounds that are well resolved by helic, but should not be resolved well by a reverse phase. The later fractions, while you see some resolution, tend to be earlier eluting from the reversed phase column. So it turns out that no single set of methods is perfect at covering a reverse phase high pH versus reverse phase low pH. So it's a little bit different selectivity. And but the question, of course, is compound identifications. What does this show us? So when you compare it to an optimized, not just a standard 20-minute run with conventional loading, but a more optimized one-dimensional separation akin to what we showed in the analytical chemistry paper, we feel that you can do even better. And the data that we've generated so far is preliminary, but by combining both of these fractionation approaches, we get yet more identifications than what we can get out of one of these alone or a single dimensional separation. There does become a point of diminishing returns eventually. So hopefully we've begun to demonstrate that you can get more out of your samples, and simple optimizations are good. A little bit more complex optimizations can do better. And all of this can be made more routine, we feel, and we're working to demonstrate that. Of course, what we'd like to do is still to build that bridge between LCMS and NMR, and we think that this 2D fractionation is the beginnings of doing that as NMR gets better, and as we become more comfortable with what needs to be done to get truly closer to pure isolates from the LC dimension. You're never going to get there entirely. We feel we're becoming closing. We don't solve all the challenges of compound ID, of course. So NMR computational methods still very important. And the automation of these methods are kind of a critical challenge. If we ever want to see this adopted, we need to demonstrate that this can be done by an average or at least an LC savvy lab without too much difficulty and without too much expense in terms of time beyond what you might already be spending trying to identify samples in the data analysis workflow, which we posit really occupies the vast majority of the time. So shifting gears, but not entirely, because how do we go about lining up data from one method, say conventional conditions, to data that was acquired under more unique conditions? We found that the tools that were out there to do that were lacking, and lining up data across labs, which has not been, exquisitely designed to be able to be combinable across batches, is a challenging process. And so Hani briefly yesterday and at various contexts over the course of the consortium has told you about this tool which he developed called Metabcombiner, which is a tool that uses more data than usual in the data. A lot of the times we try to align features by mass to charge or mass to charge and retention time alone, but we're looking at large data tables, and maybe we use some sort of fuzzy logic to align them up, but we have no real way of assessing how well that alignment worked, and we generally tend to ignore quantitative aspects of the data, relative abundance features, when we try to make that alignment. So Hani said, let's take a more systematic approach, and let's use a retention time projection approach aided by relative abundance informations divided into quintiles to say, what is the best match from one feature to the next. And so Hani yesterday told you a little bit about how Metabcombiner works. I'll direct most of the questions on the specifics of it to Hani and to Ala, who's helped with this process. But essentially, it starts by grouping features, does an initial grouping. It selects anchors in an automated way, but you can also you can do you can help it out. You can specify things that you want to serve as anchors. So you could envision using internal standards that you would put into a sample when you've got them available. And it does a spline-based fitting, looks at candidate pairings and assigns those candidate pairings a score, which I think is really a critical feature. And then ranks the features by alignment and lets you, based on your assessment of the alignment and looking at score thresholds, decide what represents a correctly aligned feature, which versus what represents one to be disregarded. And so it's really helped a lot in the context of a lot of projects. And what's coming out is the ability to align rather than data set X to data set Y, is to align an unlimited number of data sets one to another, and do all of this with a graphical interface for people like me who don't eat R for breakfast. And so Hani showed you yesterday how this helped out with our in-house data analysis from the Unknown Lipids project, as well as the sort of common method data. And Hani, I'm eagerly awaiting his assistance with that final step in the Unknown Lipids project, as it's an important part of our comparison. We've done some of these alignments already, but as the data sets have been refined, we need to do this one more time. And so Hani showed you a little bit yesterday on the in-house method data, how the labs found fairly limited agreement in terms of the features that were detected. The good news is that the picture looks a good bit better when we use the common method data, when the data were processed using a common pipeline. And so I think it speaks a fair bit towards the potential of common data processing pipelines for metabolomics to improve reproducibility in feature detection. There are certain and feature alignment between labs, and there are certainly hurdles that remain to be overcome. But I think that it's shown that there is potential. So another top project that you've heard from us before about is the ability to align features. To annotate features. As Gary Patty will tell you, not all of your unknowns are things that we should be thinking of as true biological unknowns. A lot of them are degeneracies. They're adducts, they're fragments, they're things that we might not expect. And so we can get a little bit lackadaisical about this as chemists or as metabolomicians, in that most software these days at least make some attempt to annotate adducts, annotate fragments and clean up your data in that way. However, the job is not done, as I think Gary Patty, not to speak for Gary, would tell us. You can use really cool tricks like Gary was able to do when you can grow E. coli in uniformly C13 labeled media and look for features that are labeled versus unlabeled versus not conforming to that pattern. But if you're not dealing with E. coli or something that can be grown on a fully C13 labeled nutrient source and yield fully C13 labeled samples, you need another approach to work on all those other unknowns in your samples. And this bitter is not the only show in town here, but we think it's a good one in that it considers things from two different angles. It considers adducts, and including higher order adducts, not just a sodium adduct or a potassium adduct. It looks at a good number more potential alignments, and also it looks at unpredicted correlations between features. So it looks at correlations between features that are co-eluding and sort of flags them as this might be something that is an adduct. And the data interpretation is still a challenge, but it is useful. And so one example of how we're using it is with the Unknown Lipids project data, where we've looked at both known adduct based on mass shifts, and we've looked at correlating features, and it can give you some idea of how the unknowns are breaking down. And a very preliminary report looking at one set of data shows roughly 15% of our unknowns that we've been looking at may be software predicted degeneracies. Of course, there's challenges dealing with this multi-lab aligned data set. I know my time is short, so I'll briefly mention another piece of software that we've developed. How do you keep track of it all across data sets? Do you, a lot of this is, these steps are challenging, and there's no substitute, unfortunately, for human eyes in annotating features when you're trying to do a good job. So we set about developing software that would help sort of put all of these compound identification related steps into a single package, not to be confused with the data alignment software or data quantitation, just focused on compound identification. And the result is MetID Tracker, which is a tool that you can download a beta version of right now. It has useful features like putting a front end on NIST MS PEP search, a spectral visualization, and the ability to assign features at a much more granular level of detail, whether you're looking at adducts or fragments, whether you are looking at features that need more work in terms of higher quality spectra. It allows you to filter your features and look at particular score thresholds, look at particular entropy levels. We do like that approach. Lets you look at the data visually and say, where are my adducts, where are my fragments, where are my real features coming out? And as I mentioned, it uses NIST MS PEP search, but it does more than that. It also incorporates spectral entropy. And now I don't have much time left, but to wade in my last couple of slides into a controversial area, something we think is really important is this idea of being able to assign identification confidence. And so there's been lots of different ways of doing this described. Of course, the old way is just to report identification confidence levels as proposed back in 2007 and have been refined various ways. But we all know that that doesn't really tell you, that just tells you, you're being honest about what you're reporting and what you've used to make an identification. It doesn't really tell you how confident you should be that an annotation is right or wrong. There's been other approaches proposed. Sirius has COSMIC as its proposed method for assessing confidence, but it still has this manually select higher confidence rankings step in the workflow. So it's not really a confidence estimation. So something we've been working on, and hopefully we'll have a flavor of this in the upcoming version of MetID Tracker, is using multiple inputs, not just a score, not just a threshold, but multiple factors to help assess identification. And the controversial part is there may yet be a role, albeit not a exclusive role, for decoy-based database searching in helping to assign identification confidences. And that's something we've debated a lot in our CIDC calls. And we definitely don't believe it's the whole answer, but we believe it can be part of a strategy. And I think that this, as a group, is really where we still need to spend a lot of our time working, is how can we take all of these great tools and features and data set to ultimately generate an identification confidence estimate. I've already told you about what's wound up taking up a lot of our time and been really one of the most fun part of things that we've done here, but just wanted to acknowledge the contributions of everyone to the unknown lipids and polars and internal standards projects that we've had the privilege of leading here. I look forward to getting these publications out in the near term and continuing these collaborations in the future. And then I should say thank you to everyone who's contributed, both at U of M and elsewhere, and to all of you for your attention and for listening to me, helping me learn a lot through this whole process. Thanks.
Great. So that's pretty much right on time. I mean, we could probably entertain one question or have it go into the chat. Okay. Well,